Well, welcome back to our course, Networks and Distributed Systems, based on the textbook by Jim Caros and Keith Ross, Computer Networking, a Top-Down Approach. We just learned how ISPs use RIP and OSPF to determine optimal paths for source-destination pairs that are internal to the same autonomous systems. Let's now examine how paths are determined for source-destination pairs that span multiple autonomous systems. The BGP protocol version 4 is the de facto standard for inter-autonomous system routing protocol in today's Internet. It is commonly referred to as BGP4 or simply BGP. As an inter-autonomous system routing protocol, BGP provides each autonomous system a means to 1. Obtain subnet reachability information from neighboring autonomous systems. 2. Propagate the reachability information to all routers internal to the autonomous system. And 3. Determine good routes to subnets based on the reachability information and on autonomous system policy. Most importantly, BGP allows each subnet to advertise its existence to the rest of the Internet. BGP makes sure that all autonomous systems in the Internet know about the subnet and how to get there. If it weren't for BGP, each subnet would be isolated from the rest of the Internet. BGP is extremely complex. Nevertheless, because BGP is an absolutely critical protocol for the Internet, it is the protocol that glues the whole thing together. In BGP, pairs of routers exchange routing information over semi-permanent TCP connections using port 179. The semi-permanent TCP connections for the network looked at earlier are shown here. There is typically one such BGP TCP connection for each link that directly connects two routers in two different autonomous systems. Here we see a TCP connection between gateway routers 3A and 1C and another TCP connection between gateway routers 1B and 2A. There are also semi-permanent BGP TCP connections between routers within an autonomous system. In particular, this figure displays a common configuration of one TCP connection for each pair of routers internal to the autonomous system, creating a mesh of TCP connections within each autonomous system. For each TCP connection, the two routers at the end of the connection are called BGP peers. And the TCP connection, along with all the BGP messages sent over the connection, is called a BGP session. Furthermore, a BGP session that spans two autonomous systems is called an external BGP session. That's abbreviated eBGP, lowercase e, capital BGP. And a BGP session between routers in the same autonomous system is called an internal BGP session, or lowercase I, capital BGP. The eBGP sessions are shown with a solid line, and the iBGP sessions are shown with short dashes. BGP allows each autonomous system to learn which destinations are available via its neighboring autonomous system. In BGP, destinations are not hosts, but instead are CIDRized prefixes, with each prefix representing a subnet or a collection of subnets. You remember CIDR from our earlier discussion, classless interdomain routing, the addressing scheme. Then, for example, suppose there are 4 subnets attached to AS2, 138.16.64/24, 138.16.65/24, 138.16.66/24, and 138.16.67/64. Then AS2 could aggregate the prefixes for these four subnets and use BGP to advertise the single prefix 138.16.64/22 to AS1. As another example, suppose that only the first three of those four subnets is in AS2, and the fourth subnet, 138.16.67/24, is in AS3. Then, because routers use longest prefix matching for forwarding datagrams, AS3 could advertise to AS1 the more specific prefix 138.164.67/24, and AS2 could still advertise to AS1 the aggregated prefix 138.16.64/22. When a router, gateway or not, learns about a new prefix, it creates an entry for the prefix in its forwarding table. In BGP, an autonomous system is identified by its globally unique autonomous system number. Technically, not every autonomous system has an autonomous system number. A so-called stub autonomous system that carries only traffic for which it is a source or destination will typically not have one. Autonomous system numbers, like IP addresses, are assigned by ACAN regional registries. When a router advertises a prefix across a BGP session, it includes with the prefix several BGP attributes. In BGP jargon, a prefix along with its attributes is called a route. BGP peers advertise routes to each other. Two of the more important attributes are AS path and next hop, or autonomous system path and next hop. The AS path attribute contains the autonomous systems through which the advertisement for the prefix has passed. When a prefix is passed into an autonomous system, the autonomous system adds its AS number, or autonomous system number, to the AS path attribute in the header. For example, consider that figure we were just looking at. Suppose that prefix 138.16.64/24 is first advertised from AS2 to AS1. If AS1 then advertises the prefix to AS3, the autonomous system path would be AS2 and AS1. Routers use the autonomous system path attribute to detect and prevent looping advertisements. Specifically, if a router sees that its autonomous system is contained in the path list, it will reject the advertisement. Routers also use the autonomous system path attribute in choosing among multiple paths to the same prefix. The other attribute is next hop. Providing the critical link between the inter-autonomous system and the intra-autonomous system routing protocols, the next hop attribute has a subtle but important use. The next hop is the router interface that begins the autonomous system path. To gain insight into this attribute, let's again refer to this figure. Consider what happens when the gateway router 3A in AS3 advertises a route to gateway router 1C in AS1 using eBGP. The route includes the advertised prefix, which we'll call X, and an autonomous system path to the prefix. This advertisement also includes the next hop. which is an IP address of the router 3A interface that leads to 1C. Remember that a router has multiple IP addresses, one to each of its interfaces. Now consider what happens when router 1D learns about this route from iBGP. After learning about this route to X, router 1D may want to forward packets to X along the route. That is, router 1D may want to include the entry open paren X, I, close paren, in its forwarding table, where I is its interface that begins the least cost path from 1D towards the gateway router 1C. To determine I, 1D provides the IP address in the next hop attribute to its intra-autonomous system routing module. Note that the intra-autonomous system routing algorithm has determined the least cost path to all subnets attached to the routers in AS1, including to the subnet for the link between 1C and 3A. From this least cost path from 1D to the 1C 3A subnet, 1D determines its router interface I that begins this path and then adds the entry open paren X, I, close paren to its forwarding table. In summary, the next hop attribute is used by routers to properly configure their forwarding tables. We've covered a good bit of material in this one, so why don't we stop here so that we can actually go back and review this information and update our study guides. And we'll pick up when you get through.